Hello dear students, welcome back to our science class. Today we begin chapter 5, exploring mixtures and...
So before we start, we will explore every important concept till the very end because each part comes to the next, and by the end you will understand this chapter deeply and clearly. Are you ready? Let's begin. Welcome to grade 9, where every lesson becomes a journey through time. See every concept come alive before your eyes. Stay until the end and master every chapter with confidence. Like, comment, and subscribe for daily learning. Visit rehanstudio.com for new syllabus practice questions and complete exam preparation.
Example 5.1. Mass by mass percent equals 10 divided by 100 times 100, which is 10%. So, mass by mass percent is 10%. See how neat? Mass by volume percentage. This method is used where measuring the volume of a liquid is easier than weighing it. Second type, mass by volume. We use it when it is easier to measure a liquid's volume than to weigh it. Mass by volume percentage. It is common in medicines and laboratories. For example, a 5% glucose solution, very common in medicines and labs. Mass by volume percentage. It tells how many grams of solute are present in 100 milliliters of solution. It answers a question. How many grams of solute are in 100 milliliters of solution? Mass by volume percentage. The formula is mass by volume percent equals mass of solute divided by volume of solution times 100. Example 5.2. 5 grams of glucose is dissolved to make 100 milliliters of solution. Dissolve 5 grams of glucose to make 100 milliliters of solution. Example 5.2. Mass by volume percent equals 5 divided by 100 times 100, which is 5%. So, mass by volume percent is 5%. Easy. Volume by volume percentage. This is used when two miscible liquids are mixed. Third type, volume by volume. We use it when we mix two liquids that do mix together. Volume by volume percentage. It is common in perfumes, cosmetics, and vinegar. Common in perfumes, cosmetics, and vinegar. Volume by volume percentage. It tells how many milliliters of solute are present in 100 milliliters of solution. It answers a question. How many milliliters of solute are in 100 milliliters of solution? Volume by volume percentage. The formula is volume by volume percent equals volume of solute divided by volume of solution times 100. Example 5.3. 1 ml of pesticide is mixed to make 100 ml of spray. Mix 1 ml of pesticide to make 100 ml of spray. Example 5.3. Volume by volume percent equals 1 divided by 100 times 100, which is 1%. So, volume by volume percent is 1%. Note, industries commonly use weight by weight percent. Numerically, mass by mass percent and weight by weight percent are equal. Industries often say weight by weight percent. Numerically, they are the same thing. Don't panic over the different names. Threads of curiosity. A hospital saline drip is usually 0.9% sodium chloride, or common salt, in water. That drip bottle in hospitals is usually 0.9% sodium chloride in water. Threads of curiosity. 0.9% saline means 0.9 grams of salt in 100 ml of solution. It simply means 0.9 grams of salt in every 100 ml of solution. Threads of curiosity. 0.9% saline is safe for blood and replaces lost fluids in the body. Why 0.9%? Because it matches our blood safely and refills the fluids our body has lost. Clever medicine. Pause and ponder. A talcum powder contains 4% zinc oxide, an antiseptic. How much is in 300 grams of powder? Try this. Hint: there are 4 grams in every 100 grams. Pause and ponder. Orange juice concentrate. 2 15 ml tablespoons in 150 ml of juice. Find the volume by volume percent. Try this one. Pause and ponder. Vinegar is 5% acetic acid. How would you make it from glacial or 100% acetic acid? Try this one too. Solubility of substances. Solubility is the maximum amount of solute that dissolves in a fixed quantity of solvent, either 100 ml or 100 grams, at a given temperature. It is the maximum amount of solute that will dissolve in a fixed quantity of solvent at a given temperature. Solubility of substances. A solution that cannot dissolve any more solute at that temperature is called a saturated solution. When a solution can't dissolve even a pinch more solute at that temperature, we call it a saturated solution. It is full. Solubility of substances. We mention temperature because the solubility of a solid solute in a liquid generally increases with temperature. For most solids in a liquid, solubility increases as you heat it. Sugar dissolves faster in hot tea. Solubility of substances. For gases dissolved in liquids, solubility generally decreases as temperature increases. Be careful. For gases, it is the opposite. Solubility decreases as temperature rises. That is why warm soda goes flat faster. Solubility of substances. Solubility is an important property used to separate substances from mixtures. Here is the big deal. Solubility is a property we cleverly use to separate substances from mixtures. Keep that in mind. Activity 5.2. Represent solubility graphically using water as the solvent and compounds A and B as the solutes. We will show solubility as a graph using water as the solvent and two compounds A and B. Activity 5.2. A graph of solubility versus temperature is called a solubility curve. A graph of solubility versus temperature has a special name, a solubility curve. Activity 5.2. On the curve, the x-axis is temperature in degrees Celsius, and the y-axis is solubility in grams per 100 grams of water. On this curve, the x-axis at the bottom is temperature. The y-axis on the side is solubility in grams per 100 grams of water. Activity 5.2. Predict from the graph which compound, A or B, dissolves more at a given temperature. From the graph, predict which compound, A or B, dissolves more at a chosen temperature. Activity 5.2. Fill in the blank. How does the solubility of A at 20 degrees Celsius compare with at 60 degrees Celsius? Fill in the answer. How does the solubility of A at 20 degrees compare with at 60 degrees? Activity 5.2. Fill in the blank. How does the solubility of B at 20 degrees Celsius compare with at 60 degrees Celsius? Fill in the answer. How does the solubility of B at 20 degrees compare with at 60 degrees? Activity 5.2. Fill in the blank. Whose solubility increases more with rising temperature? Fill in the answer. Whose solubility shoots up more as the temperature rises? Think ahead. What happens if you make a saturated solution at a higher temperature and cool it slowly? If you make a saturated solution when it is hot and then cool it slowly, what will happen to the extra solute? A peak. It comes out as crystals. That is our next topic, methods of separation. Section 5.3 covers methods of separating homogeneous mixtures. So, how do we separate homogeneous mixtures, that is, solutions? First method, crystallization. Crystallization. Take a saturated solution of compound B, 287 grams dissolved in 100 grams of water at 60 degrees Celsius. Imagine 287 grams of B dissolved in 100 grams of water at a hot 60 degrees. Crystallization. On cooling to 40 degrees Celsius, the solubility of B is 241 grams per 100 grams of water. Now cool it down to 40 degrees. At 40 degrees, water can only hold 241 grams of B. Crystallization. Only 241 grams stays dissolved. The rest separates out as a pure solid, often as crystals. So, what about the extra 46 grams? It can't stay dissolved. It comes out as pure solid, often as beautiful crystals. Crystallization. A crystal is a solid made of particles arranged in a regular geometric pattern. A crystal is a solid whose particles are arranged in a neat, repeating geometric pattern. Very organized particles. Crystallization. Everyday crystals include rock salt crystals and candy sugar or mishri crystals. You have seen crystals. Rock salt and mishri are everyday examples. Crystallization. Snowflakes are crystals, formed when water vapor freezes in the air. Even snowflakes are crystals, formed when water vapor freezes in the air. Nature's artwork. Crystallization. Frost on windows forms when water vapor turns into ice crystals. Frost on a cold window pane is also ice crystals, formed when vapor turns straight to solid. Crystallization. In labs, crystallization is the process of forming crystals from a saturated solution. So, in the lab, crystallization is the process of forming crystals from a saturated solution. Crystallization. It can separate two solids, where one is present in a small quantity and both dissolve in the same solvent. It is useful to separate two solids when one is present in a tiny amount and both dissolve in the same solvent. Crystallization. It is also used for purification of solids. It is used to purify solids, to make dirty solids clean. Crystallization. Its principle is based on differences in the solubility of a substance at different temperatures. Its whole principle rests on one idea. A substance has different solubility at different temperatures. Activity 5.3. Collect copper sulfate, also called blue vitriol. If it is unavailable, use common salt. Let us grow crystals. Collect copper sulfate. No copper sulfate? Common salt works too. Safety first. Copper sulfate is toxic. Work under adult supervision and don't touch it with bare hands. Copper sulfate is toxic. Work only under adult or teacher supervision and never touch it with bare hands. Activity 5.3. Take 1 gram of copper sulfate in a 100 milliliter beaker. Add 25 milliliters of water and a drop of dilute sulfuric acid. Take 1 gram of copper sulfate in a beaker, add 25 milliliters water, and 1 drop of dilute sulfuric acid. Activity 5.3. Gently heat in a water bath while stirring. The sulfuric acid prevents unwanted reactions for pure crystals. Warm it gently in a water bath while stirring. That drop of sulfuric acid stops unwanted reactions, so we get pure crystals. Safety first. The teacher should add the sulfuric acid. Handle it very carefully. The teacher should add the sulfuric acid. It must be handled very carefully. Activity 5.3. Gradually add more copper sulfate until the solution becomes saturated. Keep adding a little more copper sulfate until no more dissolves. Now your solution is saturated. Activity 5.3. Filter the hot solution to remove insoluble impurities. Collect it in a clean beaker and cover it with a watch glass. Filter the hot solution to remove insoluble dirt. Collect the clear liquid in a clean beaker and cover it with a watch glass. Activity 5.3. Allow the solution to cool slowly and undisturbed to form larger, shiny, well-shaped blue crystals. Now be patient. Let it cool slowly and undisturbed. Slow cooling gives bigger, shinier, well-shaped blue crystals. Activity 5.3. Filter the crystals, rinse them with cold water, and dry them on a watch glass. Finally, filter out the crystals, rinse them with cold water, and dry them on a watch glass. Admire your work. Note: sulfuric acid is required for the crystallization of only some salts. That sulfuric acid step is needed only for some salts, not all. Activity 5.3. You may also place 1 to 2 milliliters of the saturated solution on a glass plate and leave it to crystallize. Another way. Put 1 to 2 milliliters of the saturated solution on a glass plate and just leave it. Crystals will form as it dries. Crystallization. Crystallization is a common technique to separate pure substances, that is, crystals, from homogeneous mixtures. Crystallization is a common way to get a pure substance out of a homogeneous mixture. Crystallization. New compounds often come with impurities. Crystallization separates the pure substance from them. New compounds usually come with impurities tagging along. Crystallization separates the pure part from the impurities. Think as a scientist. Rapid cooling in ice-cold water gives smaller, less well-formed crystals than slow cooling at room temperature. Here is a hypothesis to test. Cooling quickly in ice water gives smaller, rougher crystals than cooling slowly at room temperature. Pause and ponder. Which of two equal saturated solutions of A and B deposits more solid when cooled from 80 degrees Celsius to 60 degrees Celsius? A puzzle. Two equal saturated solutions of A and B, both cooled from 80 to 60 degrees. Which one drops more solid? Check the solubility curves.
Pause and ponder. Does common salt crystal size change if the rate of evaporation is increased or decreased? A puzzle. Does a common salt crystal size change if you make the water evaporate faster or slower? Activity 5.4. Describe how salt crystals are obtained from seawater. Seawater, then a saturated solution, then salt crystals. Explain the chain we all know. Seawater, then let the water evaporate, gives a saturated solution, and then salt crystals. That is how coastal farmers make salt. Ready to go beyond. Large natural crystal deposits occur in mines, caves, and within the Earth's crust. Nature grows huge crystals too. Inside mines, caves, and deep in the Earth's crust. Ready to go beyond. For example, the Masmai cave in Sora, also called Cherrapunji. Quartz is a beautiful, naturally occurring crystal. For example, Masmai cave in Cherrapunji. And quartz is a gorgeous crystal that forms naturally. Bridge to distillation. When we evaporate a solvent to get a solute, like salt from a salt solution, the solvent is lost. Notice a limitation. When we evaporate water to get salt, we lose the water. It escapes as vapor. Bridge to distillation. To recover the solvent as well, we need another method. But what if we want to keep the solvent too? We need a smarter method. Bridge to distillation. Here is a problem. How do we separate two miscible liquids, such as accidentally mixed acetone and water? How do we separate two liquids that mix completely, say acetone accidentally poured into water? Enter distillation. Distillation. Distillation separates two miscible liquids by heating until the lower boiling liquid vaporizes, then cooling the vapor back to liquid. Distillation separates two miscible liquids by heating. The liquid with the lower boiling point turns to vapor first. Then we cool that vapor back into liquid. Distillation. It allows recovery of the solvent, or separation of liquids that differ in boiling point by at least about 25 degrees Celsius. Its great advantage: we recover the solvent too. It works when the two liquids' boiling points differ by at least about 25 degrees. Distillation. It can also separate a liquid from a solution containing dissolved solids. It can also separate a liquid from a solution that has dissolved solids in it. Distillation. In the process, vapors of the lower boiling liquid pass through a condenser and are cooled by water or air. The vapor of the lower boiling liquid travels through a condenser, where water or air cools it back to liquid. Distillation. The pure liquid, called the distillate, is collected separately. The solid or other liquid stays in the distillation flask. That pure collected liquid is called the distillate. The solid or higher boiling liquid stays behind in the distillation flask. Distillation. Know the setup parts. The distillation flask, the thermometer, the water condenser with an inlet and an outlet, and the conical flask. Know your apparatus. Distillation flask, thermometer, water condenser with an inlet and outlet, and a conical flask to collect the distillate. Distillation. Acetone and water can be distilled because acetone boils at about 56 degrees Celsius and water at 100 degrees Celsius. Why does acetone and water work? Acetone boils at about 56 degrees, water at 100 degrees. A big gap, so acetone leaves first. Distillation. A large boiling point difference lets one liquid vaporize before the other's vapors form in significant amount. That large boiling point gap is the secret. One liquid vaporizes well before the other even starts giving off much vapor. India's scientific contributions. Distillation has long been used to extract fragrances from flowers to make perfumes. For ages, we have used distillation to pull fragrance out of flowers to make perfume. Beautiful chemistry. India's scientific contributions. Kanauj in Uttar Pradesh, the perfume capital of India, captures the earthy after-rain smell as Mitti Ka Itar. Kanauj in Uttar Pradesh, India's perfume capital, even captures the earthy smell after rain as Mitti Ka Itar. India's scientific contributions. Mitti Ka Itar is made by the traditional Deg Babka distillation method passed down over generations. Mitti Ka Itar is made using the traditional Deg Babka distillation method, a skill passed down over generations. India's scientific contributions. The Fragrance and Flavor Development Center in Kanauj separates fragrance components and supports farmers. The Fragrance and Flavor Development Center in Kanauj separates fragrance parts and supports local farmers. Science plus heritage. Ready to go beyond. A petroleum refinery processes crude oil into useful products like petroleum gas, petrol, kerosene, and diesel. A petroleum refinery takes crude oil and makes many useful things. Petroleum gas, petrol, kerosene, diesel, and more.
Keep adding sugar, and eventually, no more will dissolve. That's a saturated solution. Heat helps solid dissolve, but it drives gases out. During Zvinnerfrei si sforsio entisint, the stunned, it drives gases a scout. As it cools, pure crystals grow. This is crystallization. Boil the liquid, then cool the vapor back down. That's distillation. When boiling points are close, a tall column splits crude oil into petrol, diesel, and kerosene. Wanting to be no iperosomes, solcutins to ferding, forn of light to rackagation. And that brings us to the end of part 2. Well done, dear students. You have taken another big step in understanding mixtures and their separation. In the next part, we will go even deeper, so don't miss it. If you enjoyed this slide, like this video, drop a comment with your questions and share it with your friends. Keep learning, stay curious, and I'll see you in the next part. Take care and happy learning.